And for every flow coming in, you have the flow rate, the enthalpy of that stream, and then for every flow coming out, you have the same thing. Does this look familiar? We'll put up some definitions, even though you're probably familiar with them. So rate of heat flow in the system. If this is 0, what do we call it? Adiabatic, right? I mean, yeah, steady state as well. Now, steady state would just imply that Q dot's not changing, right?
I thought you just meant dEdt.
Oh, sorry. Yeah, this is steady state. All these other things can be changing. But yeah, if Q is 0, you're going to solve a lot of problems for adiabatic systems. So again, we have these conventions we have to worry about. So this shaft work is done by the system. Of course, that's not usually how it works if I have an impeller. But that's why it shows up as a minus sign right there instead of a plus. I'm not going to put them up here, but Fi naught and Hi naught are the same things, but not in the exit, but the inlet. Right? You guys get that. Okay, so some comments, some simplifications that we can make kind of early on. Usually the kinetic and potential energies can be neglected. Since those terms are usually much smaller than the internal energy, right? And really what matters more here is that the changes in those terms are much smaller. Even if you have a lot of kinetic energy, if it doesn't change in the inlet and the outlet, it's not really going to make a difference. But what are we changing when we're doing chemical reactions is we're changing the internal energy. So the enthalpy includes the flow work. By the pressure and the volumetric flow rate. I didn't really put that there. All right, and then the assumption that we are going to make for a CSTR or a PFR is what? Steady state. So that's for a CSTR or PFR or a packed bed reactor. Any flow reactor, right? Continuous flow reactors. We don't have to worry about accumulation rates. All right, so let's look at reaction. The reaction we always use. We'll assume irreversible. So we don't have to worry about one rate. Okay, so what did we do when we were in the stoichiometry chapter? So a little bit of review. Everybody's talking really fast. Divide by A. And how do I choose which one is A? Is it the one that I wrote down first on the exam? No, it's the limiting reactant, right? So make the stoichiometric coefficient for limiting reactant to 1, meaning often. So the inlet flows times the molar enthalpies is what? It's just going to be the sum, right? So it's FA naught times the molar enthalpy of A in the inlet Anything else? Could anything else be flowing through my reactor? And then, of course, you'll have the same thing for the exit stream. Right?
Is one of those 0, depending on which one's
It's one of them 0.
going out? If A was the little maybe.
Only if I ran it all the way to 100% conversion of A. Right? Just because it's a limiting reagent doesn't mean that we consume all of it. It just means that it would run out first. And most of the time, we don't go to 100% conversion, right? I don't think we've had any problems like that. Because it's a really bad way to run a unit. Because it takes a very large reactor to go to 100%. It takes a much smaller one to go to 95%. And then you can just do some separation. Okay, so we want to express the flow rate of the species in terms of what? And then what initial flow rate do we want to use? Yeah, the initial flow rate of A. And then how do we relate the initial flow rates of B, C, and D to the initial flow rate of A? I'm going to assume everybody said big theta. So FA is equal to FA naught times 1 minus x, right? So far, nothing's different. FA naught times what? Big theta b. We don't need the knots here. Sort of the definition. Minus b over a times x. I think you guys know how to do it for C and D. What's I? You still want to write it in terms of FA. No. That way all you have to do is take your problem statement and figure out what the inlet flow rate of one compound is. Alright, so if we go back to this equation, or no, we're going to take the difference between these two actually. So if we take the difference between these two equations, we get FA naught, HA naught, plus FA naught, theta B, HB naught, right? FA naught, theta C, HC in the inlet,